For that, I would like to give a small introduction video about VÆRIDION. Right, so meet the aircraft we're developing, meet the Microliner. It's a 100% battery electric aircraft designed for regional flight. It's a 9-passenger aircraft. It's a CS23 certification pathway. We'll get back to that a bit later. I'll explain you why it's CS23. In terms of range, 400-kilometer range plus reserves, which can serve roughly 80% of the regional flights that are happening with turboprop aircraft today. And there's versatile use cases as well. So we're looking at commercial, we're looking at business, maybe cargo, maybe air ambulance. I'll give a bit of an examples later as well. So quickly about the sustainability indicator. So there's a reason why it's battery electric aircraft, because we want it to be sustainable. We have a climate crisis. So if we look at the statistics or the performance there, so energy efficiency, depending on the load factor from an LCA analysis, 110 to 180 watt-hour per passenger kilometer. That's more efficient than an electric car when we look at typical load factors. If we look at the climate impact, 33 grams of CO2 emissions per passenger kilometer. If we compare that to the most efficient, lowest emitting aircraft that is flying out there today commercially, A320neo, we have roughly 5 times lower emissions. Also, we have a noise reduction, of course. So sustainability does not only come with greenhouse gas emissions, there's other aspects as well, and noise is one of them. We did a study, I'll show you later. We'll get to roughly 10 a weighted decibel reduction. So it's roughly half the perceived noise on ground. Now, I mentioned 400 kilometers range, including, or let's say, plus reserves. I would like to dive into that a bit deeper to give you a better understanding. So when people talk about range, they do not always have the exact same understanding. So what we see here is a battery electric CS23 aircraft ideal range example. So it's relatively simple. On the bottom, you can see the Brickway range equations for battery electric aircraft. And basically, there's 3 major effects going in. It's the electric propulsion system efficiency, it's the aerodynamic efficiency, and it's the structural integration efficiency. In this case, the structural integration efficiency is basically the mass of the battery over the total mass of the aircraft. On vertical lines, you will see on the x-axis, you see the maximum takeoff mass. And in vertical lines, I've drawn 2 limits that we're currently seeing within the CS23 regime. So we see a 5.7 ton limit, which is the limit for EASA wet switches from other than complex to a complex aircraft. And at the same time, you also see a threshold here for security measures at airports. So when you're below 5.7 tons, you have lower restriction or lower security measure needs on smaller airfields. Second line is the CS23 limit, so it's at 8.6 tons. This is the absolute limit for CS23 aircraft. When you go over that, you need to go to the CS25 class. On the y-axis, we see the ratio between the operating empty mass versus the maximum takeoff mass. Here I've drawn a line at 0.5. Basically, anything above 0.5 is what we're currently seeing as a typical ratio for existing aircraft. This is important to note because we cannot just endlessly put batteries on an aircraft. There is, of course, an airframe around those batteries. So looking at it from a realistic perspective, we can only look at a certain weight ratio or operating mass ratio with respect to the maximum takeoff mass that is kind of above 0.5. So typically we're seeing about 0.5 to 0.7. Now, if we plug in some values like I did here, which result in this graph, they're listed on the bottom right. So we have a payload of 1,000 kilo, which corresponds to the payload of the microliner. We have a battery energy density of 280 watt hour. This is kind of state-of-the-art industrial battery cells as you see them today. Here we're talking on pack level when the battery is integrated. So if we take roughly 20% integration factor, we get to roughly 350 watt hour per kilo on cell level. This is what we see today on an industrial production scale, which has enough cycles that's able to sustain enough flights before the operator needs to replace those batteries. Anything that is higher typically means it's a battery cell that comes out of a laboratory, so it's not able to sustain the amount of cycles, or it's a specific cell meant for a specific application, which can have implications on, for example, the charging time, so how long it takes to charge may take much longer, or the cycle life as mentioned. Propulsive efficiency, pretty straightforward. And then we get to the L over D. So we have 22 here. And this is an L over D for a aerodynamically optimized aircraft. So this means that we've kind of made long, slender wings, aerodynamic efficient. Our aircraft currently is actually a bit above 22, so we're playing it safe here in that sense. But I want to use this value to give you an idea. So if we look at the contour plot here, we will see that the energy density on pack level together with the L over D results in an ideal range of around 450 to 650 kilometers, right? So this is for a highly aerodynamically optimized aircraft with current day technology, the maximum range. So anybody who claims that they can do more than that, you should get question marks. Why are they able to achieve that? Because with current day technology, that may not be the case. Second thing that I want to highlight is that this simple ideal range has a certain implications when we go to the real world scenario. So here I plotted the simple flight. So we have a few cruise phases, a few flight phases, 1 to 9. As you can see, I've indicated 100%. So we can use the entire battery for this one flight. However, when we switch to the real world regulations to be able to fly the actual flight, we need to add something, which is 30 minutes of loiter. So we take a non-commercial VFR day flight, so a flight that takes place in daytime, and we already need to account for 30 minutes of loiter. This is written by regulations, but when we do the energy planning for the flight, we need to account for it. So we already see that now, instead of using 100% of the energy that we have originally on board, we can only use 80%, 87%. The other 13% disappears into this holding, which in a typical flight you will not be using, but neither can use it to actually get somewhere. Now let's step it up one day, and maybe our pilot would like to fly at night. Instead of 30 minutes, now suddenly we see we already need to account for 45 minutes of loiter. So our percentages, left side's gone down again. We can now only use roughly 80%. So we already lost 1/5 of the energy we have on board just to be able to actually fly that flight. And on the other hand, holding 45 minutes, we see 19%. So we're still flying non-commercial at the time, right? But ideally, from a use case, an operator wants to fly commercially, want to fly passengers that are paying for their tickets. So let's see what that looks like. And now the picture gets even worse. So on the left side, again, we have the actual flight going from A to B. So what the passenger would like to do, what he's paying the ticket for. And we see that the energy that is available is reduced to 70%. On the other hand, on the right side, we see all the reserves that we need to account for. So we need to fly from B to C, or let's call it destination A to B is the main flight, and then going from destination B to alternate destination C, in case of an emergency or in case you're not able to actually land at the originally intended airport, already costs you roughly 30% of the energy on board. So I'm highlighting this again because when an aircraft manufacturer or a certain aircraft concept tells you, hey, on a maximum range, we're able to fly 600, 700 kilometers, A, you may have a question mark whether that's future technology batteries or whether that's current day. But B, we also need to look at, is it actually a useful real world use case? Because it's indicated here, we actually lose a lot of energy. So from that 600 kilometer, maybe the actual flight range that is useful for commercial flights reduces to maybe 400 kilometer. At the same time though, 400 kilometer is still a very good range. So what you see here is a map of Europe. And we've indicated all the airports. We have roughly 3,300 airfields in Europe. As you can see, quite nicely distributed as well. 2,300 have a sufficient runway length. That's for our specific aircraft in this case, so a 9-passenger aircraft. And we've indicated in the green dots also how many are IFR capable. IFR is important to consider because when we fly in a commercial setting, we want to be able to operate in bad weather conditions as well. Passengers don't like to have the flight cancelled just because it's raining a little bit. So as you can see, everything nicely distributed across Europe. And this makes Europe actually a very interesting market for battery electric flight because there's a lot of airfields, airports that can be connected with battery electric flight. And as already indicated before, 400 kilometer actually brings you to 80% of all the turboprop aircraft flights today. So quick example here, we have two circles to give you an impression of what it means to be able to fly 400 kilometer. Now this 400 kilometer includes a certain alternate destination. Depending on favorable conditions, you may be able to get to 500 and still have enough reserves. That's why I've also indicated a 500 kilometer range circle here. You can see a lot of destinations in this example in Norway, for example. So Norway is a specific example because there's a lot of fjords in the coastal area where it can take quite some time to be able to travel by car. Possibly there's no public transport at all. So these are typically public service obligation routes. So the government is actually subsidizing these routes. Why? Because that's the only way for those people without a car to get from one city to the other. Another example, in this case in Paris, Le Bourget, we can also connect a lot of airports in a different setting, in a business setting maybe. So let's say certain business travelers, they're in Paris and they need to meet a certain client or a certain company outside. Then this would also be a sustainable way for them to travel there instead of taking a more polluting conventional aircraft. Quickly switching to the US. US is a very similar story. Also, there's a lot of airfields distributed across the country. There's a lot of airfields, so 4,800. They tend to have a bit longer runways apparently because we still have 4,500 left for our aircraft. And quite a few are still IFR capable as well. So similar story there. Now, for us, of course, this is what the market is. This is what we're kind of looking at when we're designing the aircraft. But are people actually buying and interested in the aircraft? So yes, to that we have our first launch customer. So we have the ASL group. We have a binding sales agreement with them, and at the same time we have a lot of letters of intent currently signed for a lot of other aircraft. So we also have something which is what we call the market advisory committee. So we have our impression of what the market looks like and what we're designing for, but is that actually true? So that's why we started a market advisory committee, where you can see some of the selected members on the logo on the page here. Basically, in the end, battery electric flight or sustainable flight or regional air mobility is going to be an ecosystem. We, as an OEM, we are only one player in that ecosystem, but it consists of much more. It consists of operators and airlines. It consists of airports, but also aircraft financiers and lessors, because somebody needs to have to provide sufficient means to buy those aircraft before they can go to the operator. With pilot training, for example, battery electric aircraft is a kind of a new way of flying, so we need training to be able to train the people, of course. So with aircraft maintenance as well, the aircraft needs to be maintained just like a conventional aircraft, a bit less thanks to our electric engines, but definitely we need to prepare a whole ecosystem to be ready for battery electric flight. So this works two ways. We get their experience and their input, so we can tweak our aircraft design accordingly, make it easier for them, but vice versa, we can share our knowledge and information with them as well so that they can start preparing for battery electric flight. All right, coming back to the certification aspect. So I told you before, it's a conscious decision, CS23 level 3. So I'm going to try to explain to you why that is. So on the bottom, we see CS LSA, so it's the light sports aircraft. So currently there is a battery electric aircraft called the Velis Electro from Pipistrel is certified, so it can fly with 2 people. It's a very nice step. We're very happy that that's happening because it can introduce people to battery electric flight already. You can do your pilot training, for example, in that aircraft. But of course, from a commercial setting, you cannot fly passengers somewhere. Then on the other extreme end, we have CS25. So that's the upper one. These are the large aircraft that you know. So ATR, Airbus A320. It's very strict regulation. So they're big, they transport a lot of passengers, but therefore also the governed by very strict certification regulations from EASA. And then in the middle, we have the medium-sized aircraft, if I may call it like this. So let's say 6 to 9 passengers for CS23 level 3. And one of the benefits here is that they can transport passengers up to 9, so we can create a meaningful business case. But at the same time, they have a benefit of a reduced regulatory burden. So when we look at CS23 level 4 and CS25, they need to comply with a regulation that a certain failure probability needs to be less than 10 to the minus 9. For CS23 level 3, this probability is reduced to 10 to the minus 8. So that actually helps a lot in terms of bringing a new technology to the market. So we basically have an opportunity to bring battery electric flight to the market. Whereas we can prove and demonstrate this technology is ready, it's working, and from there on have a meaningful business case as well, where operators can fly the aircraft, gain experience, and from that use it as a stepping stone then up to CS23 level 4 and CS25, so the larger aircraft. So eventually we can make a pathway from the CS23 9-passenger aircraft to the larger ones to introduce battery electric flight there as well. So in this case, CS23 level 3 really forms a sweet spot between the business case, between market needs, regulatory needs, lighter certification, so less development cost for us as an operator as well. And this is why we see a big contrast with the eVTOLs again. So the eVTOLs, meanwhile, have accumulated billions and billions of euros to get something flying, which they've successfully done, but they have not successfully certified it yet, and they're not in operations yet. And this is where we see a clear benefit with a conventional aircraft like the Microliner, where it costs a lot less money or euros or dollars to get it to the market in a certified way. So the aircraft design for our side is completely clean sheet design. Has a few reasons. Listed them here. So on the one hand, we've talked about range. We want to maximize the aerodynamic performance of the aircraft in order to maximize the range. So this is L/D you saw in the range example. Our aircraft has very long, slender wings, up to 24 meters. So for a typical aircraft in this size, maybe you will see around 12 to 17, 18 meters, but we are going much further. We're limited there by an ICAO B-box, so there's a certain limitation. I'll come back to that later as well. At the same time, clean sheet design, instead of retrofitting, also allows us to integrate the batteries where we want to integrate them, which has two effects. On the one hand, we can get a better mass distribution, and on the other hand, we can reduce the structural weight of the aircraft. So we're integrating the batteries inside the wing, and the effect of this is that we have a lower bending moment because some of the mass of the aircraft is integrated in those wings. So we get a lower bending moment, and therefore we can get a lighter structure. Lastly, we've also come up with a novel propulsion system. You see a single propeller here in the nose of the aircraft, but actually behind there are two engines. So we are recognized as a multi-engine aircraft, and I'll come back to that in a bit as well. Some performance statistics, or some statistics in general. So we have the wingspan, 23.99 meters, so it's an ICAO B-box. So ICAO B-box means there is certain agreements between airfields and airports on box sizes. So let's say parking spot sizes for aircraft. And once you go over that, of course, you're going to get into, or you're going to need a bigger box, which means that there will be less airports, airfields will be able to handle you. So it's a conscious decision to stay at that limit. Which of course has a small penalty for the aerodynamic efficiency compared to going over that. But yeah, from an operational perspective, that is kind of an important factor. Maximum takeoff mass, 5.7 tons, so 5,700 kilos. The specific reason as well for this, it's because, as indicated before, this is where there's a regulatory change going from other than complex to complex, which has certain implications on flight regulations, crew training, etc. But also we're able to operate in a commercial setting for much more airfields, thanks to this lower security burden. Payload, 1,000 kilo, 9 passengers plus 2 pilots. If you look at the aircraft at the cockpit, you see that the cockpit has a layout for 2 pilots. However, the aircraft is capable of flying single pilot operations as well, so there's a cockpit designed for that. Unfortunately, if we remove one pilot for commercial setting, we cannot take an extra passengers because within the regulations there's a hard limit at 9 passengers as well for level 3 in this case. If we look at the takeoff distance, 800 to 1,000 meters, it's a little bit more than a conventional aircraft, but not much, even though we're much heavier. So it's quite good. Flight ceiling, 20,000 feet, which means we have a pressurized fuselage as well. Reason for it is that we looked at some application cases, some areas where we would like our aircraft to fly. Norway is one of them. And in Norway, there is a regulation that above mountainous regions, you need to have a pressurized aircraft. Additional for those public service obligation routes that I mentioned before, you will also need pressurized aircraft. It's written in the regulations there. So pressurized cabin to be able to meet those regulations and to be able to fly at a higher altitude, also to cross the Alps here, for example. The range at full payload, 400 kilometers plus IFR reserves, we already covered that. And a certain cruise speed, so max cruise speed 186 to 170 knots equivalent airspeed. So that's very comparable still. So we want to fly fast, we can do that. It's very comparable with the conventional aircraft in this size. Of course, the thing is that as we go to longer ranges, we need to conserve energy to be able to meet that range. So we can fly this maximum cruise speed up to, let's say, 200, 220, 240 kilometers. After that, we need to start reducing our airspeed to be able to get further. So the payload, here you have a cross section of our cabin. Payload, basically typical payload for single pilot operations, as the example shows here, is 9 passengers plus a pilot. So you can take your luggage as you're used to from a conventional flight. You have 12 kilo small hand luggage suitcase. Plus a pilot can take some stuff with him as well to fly the aircraft. The cabin itself is laid out for comfort, so we'll be flying longer range missions for 100 kilometers, which means some passengers will spend 1.5 hours in the cabin. So in this perspective, it needs to be comfortable. There's an option for a lavatory in the back as well. So yeah, basically this is optional because some airlines may not want it. We could use it for suitcase storage, for example, which you can see on the bottom right bottom right picture. In the back of the cabin, there's a dedicated area. It has to be closed off because if you want to take checked luggage with the aircraft, it's not allowed to be accessible during flight. So it needs to be closed in that sense. But that's basically where passengers, then if it doesn't fit underneath the seat in front of them, can store the luggage and the hand luggage as well as the larger suitcases. An alternative configuration would be cargo. So we did the layout for palletized cargo. Typically you see containers for larger aircraft, but these containers are actually too large to fly with our size of aircraft. So in this case, we're laying it out for palletized cargo. Yeah, basically an alternative use case where we have quite some interest from operators as well. I think if you look at the Cessna Caravan, so it's a very popular 9-passenger aircraft as well. I think at one point, if you looked at the fleet composition, I think 1/3 to almost half was in use for cargo operations as opposed to passenger operations. So definitely a big market. Then the cockpit. So cockpit, of course, very modern, state of the art. We have a glass cockpit, so we're using Garmin avionics. Interesting here to note is that even though you have the single propeller, we have the 2 engines behind it. So also what you will see here, maybe you see it better on this picture, is that we have 2 throttle levers. So the pilot sitting in the cockpit, the aircraft really seems like a dual engine aircraft where you can really control each engine separately. We'll get to that in a second as well. Alternative use case, just quickly to highlight, air ambulance would be interesting use case as well. So we did a study together with our partner Aerodienst. And an alternative use case would be Air Force logistics, for example. So of course we have a range limitation. So that's on the one hand, maybe not the most obvious choice, but on the other hand, we have a very low infrared signature and a very low noise signature. and combine that with a higher reliability, because the electric motors in that sense are less moving parts, so less prone to parts failing. And we also have a fuel independency, because when you have a local setup to be able to generate electricity, it's a lot easier than to be having to be rely on fuel somewhere in a remote location. All right, so let's talk a bit about the technology in the aircraft. So, of course, we're building the airframe and we're designing the airframe, but we're trying to keep it as conventional as possible. Means basically everything on the aircraft, flight controls, ECS. ECS has to be an electric in this case, but landing gear, all these systems, we're trying to keep them as conventional as possible, so we're able to certify as fast as possible. So we're trying to really purposely minimize the complexity on this aircraft and focus basically on two core technologies. One is the wing integrated batteries. So as you can see here, basically you can see the boxes integrated in the wing. So these battery modules are integrated between the wing spar and between ribs in the wing. It's three benefits, as I already mentioned before. It's the structural bending load that is reduced thanks to the mass of the batteries. Of course, there's volume available there within the batteries because there's no kerosene anymore. So this helps, of course, to avoid to put it in other crowded places of the aircraft. So it's a nice win situation. And lastly, it's away from the passenger. So it's outside the pressurized cabin area. So in case something happens in, let's say, thermal runaway event, it's further away from the passenger, so it enhances the safety of the passengers as well. The other technology is the multi-engine single propeller. You can see that one in more detail here. So basically, you see two engines behind each other, so engine 1 and engine 2. These engines both have an individual clutch, and these clutches connect to the same shaft. This shaft then goes to the constant speed propeller. So there is something that looks kind of a bit like a gearbox, as you would know it from a PT6 engine or from a turboprop engine. But actually, that part is used to drive all the accessories. But there is no actual gear reduction or anything in there for the propeller. Now, sorry. One of the main benefits, of course, is that we have a certain redundancy now built in because we have two engines. So this brings an increases safety. Basically, what happens when one engine fails, the pilot is able to shut it down, or it shuts down automatically. The other engine is still able to provide the power. So we lose 50% power in that case, but because the propeller is actually operating in a slightly more efficient state, we only lose 40% of the thrust. With that 40% reduction, we're still able to meet easily all of the requirements from a CS23 perspective. So in that sense, that's already a benefit. But the second thing is when we compare ourselves to a conventional twin engine aircraft, when one engine fails, you get this yawing moment that the pilot needs to compensate. So this results in extra drag or added drag for the airframe, which means that there will be a range reduction, which is not the case for our aircraft because we do not have this yawing moment. And at the same time, it also means there will be a higher pilot working load, which in our case is also not the case, because the pilot will notice that there is a reduction, let's say in thrust, but the aircraft will just smoothly keep flying forward. So this was something that we found quite important, and something that we also pitched to EASA as something that can enhance the safety. So basically here what you can see is a video of this propulsion system. So this is a 20% scaled demonstrator. Two engines. You have the front, the left engine, and the rear one. As you can see, we're simulating an engine failure here. So you see with the blue lines on the electric motor, you see that it has completely stopped rotating. But you can see that the rear engine, engine 2, is still driving the shaft all the way to the front, which is the load generator, simulating a propeller in this case. So maybe the pilot did some troubleshooting, maybe was nothing wrong in the end, so we can fire up engine 1, or not fire in the scale, we can spin it up again, and basically then continue the flight as normal. You can do the same with engine 2, so we're demonstrating here the full interdependency, that there's no interdependency, so that basically each engine independently can power the propeller. And the same for the engine, of course, we can start it up again. This is something that we showed to EASA in a pre-application contract. So the pre-application contract is a service that is provided by EASA to have certain meaningful discussions with them. Can be on a topic that you decide, and we decided to bring this multi-engine concept, so single propeller multi-engine concept, to them, basically as a de-risking exercise. So we saw the benefit, but we're not sure how EASA is going to respond to that, or how EASA is going to react to this. So of course we want to de-risk that as a company. So that's why we chose to go through the pre-application contract process. We showed the evidence to EASA. We managed to convince them. So in the end, in return, we got a written statement from them. Basically a signed piece of paper that states that they recognize this as a multi-engine concept. So that's really important, because that means now later on, when we're going to start certification process, the basis has already been set and EASA has already agreed. Second technology is, of course, the battery modules. So we've been able to acquire a building, an Oberpfaffenhofen, for this, which basically allows us to start the industrialization of the battery modules. So it's a hangar that formerly belonged to Lilium. Unfortunately, Lilium went bankrupt, but the key assets that they had, we were able to get some of those, which allowed us then to speed up the development process and start industrializing the batteries, testing and production. So kind of interesting is that batteries have a different development cycle than the aircraft itself. So batteries are complex. They have strict regulations from a certification point of view. So they're complex hardware as well as complex software. So this is very strictly regulated, needs to be developed according to certain, let's say certain procedures. But at the same time, of course, this is a completely new technology. So we have a different iteration approach where we basically design something, we build it, we test it, and then we make improvements. So we repeat the whole cycle. So what you see in the upper row here was one of the first designs. Basically consisting of two different battery modules that together form the pack. We did testing with them. We were able to demonstrate that they're working. But then based on the results, wanted to optimize further. So that's why you see on the lower row, basically, making design improvements, kind of being able to combine that into a single battery pack. Also functional testing, as well as thermal runaway testing. So what you see on the right side, bottom right, sorry, is a IR camera view from the thermal runaway testing from one of those battery packs. Well, one last remark. So this is a rather quick development cycle, and I just want to highlight the contrast there again to aircraft development cycle. The aircraft development in that sense is a relatively slow process that takes multiple years, whereas this, we're talking really about improvements that are happening on a much, much faster scale. Or maybe we can have different battery designs, different battery modules tested maybe within a year even. So it's different way of approaching it. So some pictures here. We have the first battery prototype. I think we can see the welding here from one of the colleagues. Of course, from the manufacturing, we go to the testing. So we test the prototype. Here you can see the functional testing and see that everything is working. Now, batteries by themselves, of course, typically are safe. Not so many things are happening. But to give you a bit of an insight, I want to show you a video to give you a feeling of the amount of energy that is contained in a single battery cell. Right, so what you saw there was a single battery cell, so it's kind of similar to the cells that we are using for our design. And you could see it was put in thermal runaway, so typically we heat it up until it goes into thermal runaway, and then it releases the energy from the cell. Now this was one cell. We have a lot of those cells in one pack, so it needs to be, of course, there needs to be designed in a way that is accounted for thermal runaway. So by regulations, you need to be able to contain thermal runaway within a battery pack or battery module. So here we have the older model from the battery that you saw before in the pictures. Basically, we have a thermal runaway vent again, but you can see that it's nicely contained within the battery module. At the same time, of course, from regulatory point of view, this was just one cell. You need to build it up until a large. There's a bit of an inconsistency between EASA and the FAA, or at least there has been for a long time. It's starting to converge now. Where basically up to 100% potentially of the entire battery pack needs to go into thermal runaway. You need to contain that, so the flames are not allowed to exit the module or the pack unless it's through a designated venting part. And that's what you saw here at the bottom. So you see basically the smoke coming out. So there's a designated venting part. In our case, for our aircraft, means we need to eject that overboard. So we have a dedicated part basically going away from the battery to outside the wing, so we can safely ventilate those gases, the thermal runaway gases overboard. So talking about this battery integration in the wing, I already mentioned a few benefits of integrating the wing, but it also has another implication, which I would like to give you a small insight. So one of the students at VÆRIDION, he did a small design study for a 19-seater aircraft. So this is not actually for our microliner aircraft. This is a concept study for a slightly bigger aircraft, but it gives an interesting trend. So one of the key takeaways for CS23 battery electric aircraft is that if you want to maximize the range, you want to design for your maximum takeoff mass limit. So I mentioned this 5.7 ton limit or this 8.6 ton limit. Basically, if you look at the equations above, to maximize the range, you have this mass ratio between the battery mass and the takeoff mass of the aircraft. In order to maximize the range, we can tweak the ratio, and if you can see if we rewrite it and we can look at the derivative, essentially you will see that you want to just increase the mass as much as possible, because the relative portion, let's call it like this, of the battery mass increases, while let's say the ratio for the payload to the takeoff mass, the operational empty mass to the takeoff mass stays the same, and the payload is anyhow fixed, so that will not change neither. So some equations was a lecture, so some more equations. It's a conceptual study, so it's maybe some textbook equations that you know from Torenbeek. So we're trying to work towards a wing loading diagram here, and we're trying to introduce constraints here in the wing loading diagram to show you what is the effect of introducing batteries in the wing. So we can start with writing the energy that's required for a certain flight as a function of a certain energy, as a certain mass volume, as a certain volume density and a certain mass density or mass specific energy. At the same time, we can come up with an equation that kind of estimates the amount of volume that's available within a wing for the battery integration. So it's adapted from a fuel volume equation with a slightly different factor to account for batteries in this case. Of course, we can rewrite then the electric range equation to make it or to introduce the volume specific energy. And then we can plug that into, or we can rewrite that into a wing loading constraint. You can do the two sides. So on the one end, we can put a certain volume based on the wing area that's available for battery integration. On the other hand, we know that there's a certain ratio between the operational mass and the maximum takeoff mass of the aircraft that is realistic. So we cannot go beyond that. We cannot just keep putting batteries. So it's the bottom equation, what you see. And basically, if we then look at the wing loading diagram, you see that for a typical aircraft that is conventional, you would see that the wing loading would basically be at the intersection between the takeoff distance and the landing distance. So that is the green and the blue line that you see here. Basically going from the bottom left, if you go towards that corner, you want to be in that corner, and that then dictates what should your wing area be and what should your installed power be. However, now if we introduce these two new equations for the wing loading, we can see that the wing loading reduces quite a bit for realistic values. Or in other words, this means when we want to introduce batteries in the aircraft, we will see that we actually need to increase the wing area as what you would have compared to a conventional aircraft. And this is something that we also noticed when we were developing the 9-seater aircraft, so the microliner. So we were trying to fit the batteries. We realized that we had to make extra space for those batteries in order to fit in the wing. One final remark regarding these equations. They're not the nicest equations. Why? Because you will see that besides the wing loading on the left side, there's still a weight term on the right side of the equation. So the only reason why we're able to use these equations is because we already know the maximum takeoff mass limit that we're going to design for. So if you go to CS25 class, don't use these equations. You'll not be able to apply them properly. But at least for a CS23 demonstration case like here, it helps to show you the basically the change in the wing loading and therefore the wing area. All right. One of the topics that was also listed that we would like to talk about is regional air mobility. So regional air mobility is a new form of transportation, basically using a sustainable aircraft, so battery electric aircraft, and basically creating connections between small regional airfields, basically to improve maybe the travel time, the cost of the trip, or maybe a certain convenience of the people traveling. So we did some studies into this. We've published some studies as well. You can look them up. They're all AIAA published. So the one I recommend you to look at is the one on the right. So it's the AIAA SciTech publication, because that's the latest one, and that uses our aircraft as a reference aircraft to really demonstrate the potential of regional air mobility. So basically how we approached it is that we used a document from the German government, which basically highlights the travel demand between certain cells. So they distribute, they use the NUT system. They have a lot of cells within Germany and surrounding countries, and they try to estimate for a certain year, so 2040. In this case, they try to estimate the travel demand between those cells. Now, as you can see, the neighboring countries around Germany have a rather coarse grid, but if we want to estimate the travel time, we need to take a certain point. So when this area gets too big, the calculations start to get inaccurate. So we've actually enhanced it a bit. So that's what you see here. We've introduced additional cells, and basically we analyzed over 10.4 million multimodal trips. So when I say multimodal, we basically analyze 4 situations. So we have the trip by car, we compare it to a trip by train, we compare it to a trip by commercial air transport. So that's the tickets, the way you're flying as you know it today. We compare it to regional air mobility as well. So we always go from the geographic center of one of those cells that you saw to the geographic center of another cell. But of course, keeping into consideration the way of traveling. So for train, first we need to get to the departure train station, take the train, and of course from the train station, get to the cell, the geographic center again. Same for commercial air transport. We need to go to the airport, fly, go from the airport to destination, and the same for regional air mobility. We also included real world flight routing in here. So typically you can measure the direct distance or the great circle distance from A to B, but that's not really how aircraft fly. So typically they have to follow pathways, which causes a certain overhead. So we've included that as well to make the study more realistic. And we use what is called a multinomial logit model. So basically the thing you have to take away from this is this equation, as you see it here, is basically you estimate the parameters that flow into there, and those parameters, you can see the beta C, so it's the cost coefficient, the beta T, so that's the amount of time it takes to travel, and an ASC, alternative specific constant, and this is something you can consider as a convenience factor. So in comparing the different ways of traveling, we look at the cost of the trip, we look at the time of the trip, and we look at how easy it is. And then we estimate those parameters, and basically it allows us then to come up with a certain probability for a traveler to choose a certain mode of transport. We've included all the airports in Germany with the exception of a few, well, a bunch, I should say. So, of course, everything that has an insufficient runway length, we filtered it out, cannot fly on there. Everything that's over 20 million annual passengers, we filtered that out as well. Why? Because typically those aircraft are slot restricted. In this case, slot restricted means that they have a certain amount of flights they're allowed to handle per month or per year. And of course, for them, it's more beneficial when there's a larger aircraft flying than a small 9-passenger aircraft. So we removed those as well. And then we looked at all the other remaining airfields, included them in the study. So quickly looking at the costs, we did revenue per available seat kilometer. So basically, we considered a range of price points for the tickets. Basically, we came up with an optimistic case, we came up with a baseline case, conservative case. They range from 0.3 to 0.8 roughly, so you'll see later in the results that that's the steps that we show the results for. But I want you to focus on one thing and remember one thing here, and that is the relative magnitude of the battery replacement. So it's roughly 15 to 20% is the battery replacement cost for the total let's say cost for the operator of a certain trip, or like certain flight costs. Let's call it like this. I'll come back to that in a bit. Then one thing to highlight is we also investigated 2 different cruise speeds. So one cruise speed is the minimum flight time strategy. So basically, we do a certain energy planning to get somewhere, and we just try to fly as fast as possible. So the aircraft has a certain maximum speed. That's the red line you see on top. For a certain distance, we can fly this maximum speed. And then we need to start following. We need to start reducing that speed, that cruise speed, and we need to follow one of those black lines. Now, we've already saw in the previous graphs, we need certain reserves. The certain reserves means flying from B to C. B to C is situation or flight specific. Depending on where you want to go, there may be an alternative airport close by or further away. So we need to consider that as well. But what we see eventually, as we reduce the speed, we get to the eco speed. So this is a certain speed that is the most energy efficient. Now, why do we investigate those 2 cruise speeds? The hypothesis behind this, on the one hand, the passenger wants to be at his destination as fast as possible and is willing to pay for that. So the operator can make some extra money there. On the other hand, the operator needs to let's say the more energy is drawn from the battery, the faster they age. So the more often they need to be replaced. More replacement means more replacement costs. So operator loses money. So that's why we investigated both. Basically, you can see some of the results here for the different price points. So on the x-axis, you see the different price points per seat kilometer. And on the on the x-axis and on the y-axis you can see certain parameters. So we can see the number of travelers, and we can see as the price point increases, we lose roughly 19 to 13% of the travelers in total on the total network. You can also look at the number of routes. The number of routes already decreases less because even though there's less passengers, we can still operate on that route, but less frequently. So naturally, the routes drop out less fast than passengers do. And we can see the number of connected airfields. One airfield has multiple routes, of course, so they drop even less fast. But the number of aircraft required scales again with roughly with the number of travelers. So for each increase, basically we see a decrease in number of travelers. Now for us, typically we look at the 0.5 case. So if we look at the cost estimate of how much it costs to fly the microliner, we're around the 0.5 euro per seat kilometer point. What you see here is the total revenue. Now, if you come back to this number that I told you to remember, so 15 to 20%. If we see the difference in revenue on a network level between the minimum flight time strategy versus the minimum energy cruise strategy, we can see that the difference is roughly 19 to 24%. In other words, the difference that we lose in revenue is much bigger already than what we would, in the very best case, potentially gain with battery replacement by flying slower. So there's a clear insight. From an operator perspective, you always want to fly as fast as possible because the operator or the revenue that is generated on a network level is just higher. So what can a network actually look like? That's what you see here. So basically, within Germany, naturally, you see a lot of routes. You see routes decay as well as we go from the as we go to the different price points. But what is important to highlight here that even though typically regional air mobility only focuses on one country or the inner flights within a country, what we can see clearly here is that actually a large part of the flights or a large part of the demand for regional air mobility is actually also from international flights. So when we look at regional air mobility, we shouldn't treat it as an isolated system per country, but we should really look at Europe as a whole. Can also look at a slightly different view. So the top 30 routes, most of the routes are going from a west to easterly direction, but there is some exceptions, of course. But yeah, also as you can see here, especially on the last two figures, you can see some of those international routes again popping up within the top 30 routes for the entire network. Quick overview of some other statistics. So if we look at the number of aircraft, for example, for the 0.5 euro per seat kilometer case, we still look at 2,000 aircraft. So again, we considered the cost of the trip, we considered the travel time of the trip, and we considered the convenience of the trip. And basically based on that, the outcome is that there is a very big demand for passengers to use this alternative mode of transport. Reason simply is because within Germany, there's a lot of regions that have a small airfield close by that can be used for regional air mobility, but there's not always a highway available, and definitely high-speed rail network is not always available. If we look at some other numbers, so we see connected airfields around 250 for the 0.5 case. Number of routes 1,500. So all in all, we can see that actually regional air mobility can be quite a substantial number of travelers flying in this new way of transportation. Another graph here to quickly highlight. Sometimes you have the discussion to see, okay, maybe this is something, a mode of transport that is only for the rich people. So to that, of course, we've considered the price in the assessment, right? And here you can kind of see the distribution of people that are traveling from non-business purposes or people that are traveling for business purposes. And what you see here is that there's roughly a 60-40 distribution. So actually the non-business travelers are in the majority for using this new mode of transport as regional air mobility. So it's not something that is necessarily only for the rich. It's definitely something that could be considered as a system that can benefit everybody. And the last graph on this topic, this is the modal share that we achieve compared to the other modes of transport. So you can see regional air mobility works from roughly 300 to 600 kilometers. That's kind of where it has the peak modal share. After that, we can see it starts to decay, and we can see that commercial air transport starts to increase significantly. Reason for that is that commercial air transport just flies faster. So the bigger aircraft, they fly faster. So naturally, the travel time starts to decrease for those type of aircraft on longer distances. So passengers start to switch to commercial air transport. Cool. That was a few slides regarding regional air mobility. Now, of course, to have regional air mobilities, we need to have the smaller airfields. And one of the prerequisites for these smaller airfields is that charging infrastructure is available at those airfields to be able to operate from there. So this is something that our partner Albatros is working on. They were so kind to give us a few slides that I would like to show you as well to give you a better understanding. So it's a concept study they did, what it could look like at a certain airport called Schönhagen. It's a small airport next to Berlin. Basically, when we look at the requirements, there's three major contributors. So the airport itself, of course, has a certain infrastructure, a certain layout that needs to be considered. And the OEM, so us in this case, we have a certain aircraft we want to operate. So this brings, for example, the charging power that's required for the aircraft. And the operator itself, of course, that wants to fly certain routes, so certain frequency on routes. So this gives the airport a certain energy demand for the charging. So let's look at a short video to introduce this again. All right. So what is the architecture behind this? So the airport needs to have a certain grid connection, of course, because we need energy. So that's what you see here on the top of the figure on the left. The grid connection, then that comes in a high voltage transmission, so that needs to be wound down. That's why we have a transformer station. Then the heart of the system basically at the airport is the battery energy storage system, so BESS. This is basically a buffer. So on the one hand, we can have solar rooftop, solar panels, sorry, on the rooftop, which is generating electricity. This flows into the battery energy storage system, which acts as a buffer up to the point then where the aircraft, they need to start charging. And then the energy can be drawn from this battery system. Now to charge it, there's a few power units. So basically, these are modular power cabinets that are basically allow the voltage conversion. But the reason why they're modular is because then we can use them for different charging units. So we have currently two charging standards, typically CCS2 and MCS. CCS2 is something that is used for smaller aircraft. So the pipistrelle Velis Electro that I mentioned earlier is an example of that. And larger aircraft. So for our aircraft, we use an MCS charging standard. Now, this cabinets basically allow you a modular way of increasing your charging capacity over time. So it kind of reduces maybe the investment burden that is present early on for airfields when there's not so many aircraft operating. And at the same time, also a clever way of handling the different powers required by those different charging standards. Now, another important aspect here is that this grid connection can work both ways, right? So it's not only about drawing energy from the grid, as we were definitely in the Netherlands, I'm from the Netherlands, something that's heavily playing there is currently that we have grid congestion. So even as a regular household, when you want to get a more powerful connection, it's not possible anymore because of the increase in heat pumps, because of the increase in electric cars. The current network, the network grid across the Netherlands is just not able, it's not sized accordingly anymore, it's not able to handle that. So we have kind of this grid congestion, and this is starting to play in Germany as well. And this is actually where the regional airfields can start to play a role, because they act as, let's say, a local storage system, which also means that local industry or local households, when there's an energy shortage, the airport can actually start to supply energy back to the grid to compensate for that. So in this sense, it's important that this grid connection can actually work both ways. And it's another thing quickly, or really to realize that the airports can actually play a role both for traveling, but also as a solution to the grid congestion problem that we start seeing. The next image here, you can kind of see the concept of what it looks like. So in the top view, you can see how the grid connection comes in on the top left. You can kind of see how it goes across the airport. We have the solar panels on top of one of the roofs. We have the battery energy storage system located, and then it goes to those power units, those cabinets, and then to the different chargers. You can see here on the right image, you can see basically the top view of our aircraft. And now it becomes important to realize again why there was this restriction on this wingspan, because basically, as you can see here, we need to park multiple aircraft next to each other to be able to charge them, or maybe we park them overnight. The longer we have this wingspan, of course, more issues we run into with the parking and the storage of those aircraft. And that's why we stick to a certain B-box size, IK or B-box. Now these airports, of course, getting their charging infrastructure ready, getting this electrical infrastructure ready is a new business model for them. So we have a lot of interaction with these airports, and they're all very excited to work towards battery electric flight. But another aspect is, of course, the noise for the people living around it. So we did a noise simulation. Where you can see the comparison here. So on the upper figure, I'll let it run in a second. On the upper figure, you see the microliner. So it's the noise footprint in dBA of the microliner, so battery electric, versus a typical 9-seat turboprop noise profile. So I'll let it run. Basically, what immediately becomes clear is that the noise profile of a battery electric aircraft is just so much smaller. So it's less than half the perceived noise. Also, the part around the airport, the part below where the aircraft has taken off or is landing is a lot more narrow. Basically, it means that a lot less people around the airport, living around the airport, are affected. So this is an important aspect for regional mobility again, because we really want to enable this. Of course, we do not want that all the people around the airport start to be disturbed and start complaining. So this is where battery electric flight again can make a very big difference. Cool. Last two slides. Of course, we are an OEM, and I've already showed you the market advisory committee. But one thing that is also very important developing an aircraft is strong partnership. So we're actively working together with other companies, with other suppliers, basically to get this aircraft, to get this aircraft to fly. It's definitely something that's not to be underestimated. What you've seen here is all the industrial partners, but we are also working actively together with universities and research institutes. So basically, we're doing public funded research projects there. Basically to really create an ecosystem that is preparing itself for battery electric flights. So in the timeline, we want to be able to fly our aircraft in 2028, so 2028, and we'll have a certification campaign of 2 years. So in 2030, then you'll be able to take your first flight on a commercial setting with the Microliner. Last slide I've been presenting here, of course, but it's not just only me doing this. This is there's a whole team around me. So we're currently 85 people. We started small. So as you mentioned, I was the first employee. Well, actually, there was 2 of us. So basically there was 2 first employees. So shout out to Moritz as well. But basically how you say, shout out is maybe the wrong word, but like, let's say I want to say that there's a big team around this, and together we make it work. So it's not just me, it's a team effort in that sense to make it work. Cool. That was it from my side. Thank you.
Thank you, Jasper, for a very, very detailed and very technical presentation. Fantastic getting through all those slides in such a short time. Congratulations.